Hello and welcome to today's talk for Upward Bound Advanced Math. Today we're looking at the last 6 of the daily tasks that we've been working on. So I just want to put this video out. Some of them I will kind of do completely. Some of them will be more of an insight video to try to get you to see sort of what's going on. So let's get right into it. For the first one, we're talking about a bubble. And when we have a bubble and it decides to land somewhere and not break, it lands on a flat surface, and if that surface is wet and again flat, it will turn into a hemisphere. Okay, so the question is, between these two figures, they both have a specified radius, and how are those two radii, how are they related? What's the relationship between them? Okay, so notice in this problem we have no defined values or anything. I just know that if we consider this radius here to be our original radius, so the radius of the sphere, and I might do it this way. Say that here we have the radius of the sphere. How does that relate to this one over here that's the radius of the hemisphere? Okay. So let's just go ahead and look at it. The number one thing that I know holds true is that the amount of air in each of these bubbles is the same, meaning that their volumes are the same. So I know that the volume of the sphere is equal to the volume of the hemisphere. Okay, now what does that mean? What am I going to do with that? Well, if you remember from your geometry days, the volume of a sphere is 4/3 pi r cubed. I should label that this radius is the radius of the sphere. And the volume of a hemisphere is just this divided by 2. But one big difference is that the radius is not the same. So it's going to be 2/3 pi r cubed. And this r is from the hemisphere. Okay, I want to show the relationship between these two radii. So what I'm going to do for that is I'm going to pick one, solve for it, and go from there. I'm going to solve for this one. This will be my object here, my objective. So I'll start off by multiplying by 3/4 on both sides. And let's just see what that gives us. So we've got pi r cubed from the sphere. And over here we're going to have 1/2 pi r cubed from the hemisphere. So I'm using an S for the sphere and an H for the hemisphere. And now I just want to divide by pi on both sides, which is great because there is a pi on both sides. So it cancels off of each side. So 1/2 r cubed from the hemisphere. And then to solve this one, I'm going to take the cubed root. And I'm going to try to do a little bit more than that. So I'm going to do the cubed root of both sides. We're actually going to try to find a value for that other one. So over here we get just the radius of the sphere. And a cool thing about any type of root is that I could split it up, or I could just realize that my rules for simplifying any root is if I have 3 of something in a cubed root, I can pull one of those out. So this is the radius of the hemisphere times the cubed root of 1/2. It might be worthwhile to know what the cubed root of 1/2 is. So I think for cubed root, I need to go to second, right there. So 0.779, and we'll just go to 79. So that would be enough to tell you what the relationship between the two of them is. But what does that mean? Okay, that means that the radius of the sphere is, say, 75% of the radius of the hemisphere. It might be a little bit more worthwhile to see that when that changes, sort of how that changes. So the radius of the hemisphere, if we write it the other way, we'll call that 1.26, is 1.26 times the radius of the sphere. So this one's bigger, this one's smaller, okay? And that's really all we're looking at with that first one. And there's not a great way to extend it. You could put actual values in there and say, if I knew that the radius of the sphere was this much, what's the radius of the hemisphere? That would be a decent way. But I'll leave that option to you if you choose to do this problem. All right, the next one, we're talking about a goat in the field that's tied to the shed. Shed's in the middle of the field, so like the boundaries won't become an issue. The shed is 30 by 30, and the goat is on a leash that's 60 feet long and connected to the corner of the shed. This question asks how much area in square feet does the goat have to graze? And what we talked about in class was there is an issue. Let me actually let me get the entire page in here. There does sort of become an issue of where the goat can go. I'm just going to try to make sure that my, I guess, circle is as close to that 60-foot mark as I can. Okay, that should do. And so the way that I recommend doing this is, I think a compass would be really handy for this problem, but is to make circles that show you where the goat can go. All right, so that would be, if this was just a post right here, that would tell me where the goat can go, because it could go all the way around the post, it could go in every direction, and it wouldn't have any closed off area. Now, the implication with the shed being here is that the goat cannot go here. It can't go in, on, or through the shed. It wasn't written in the problem, but we just imply that. Okay? So, with that being the case, we come into an issue at each one of the corners of the shed, because you have to start playing around with the idea where can the goat go? If it can it make it to this point right here? You know, can the goat walk around to that point? Well, it's got 30 feet there. Mind you, this is a 60-foot leash. And then it has 30 feet there. So it probably can't make it to this point. But visually, why can't it? Let's take a look at that. So we're going to put a new circle starting from here that has a 30-foot radius. Now, how could I measure that 30-foot radius? Well, it's the size of the shed. So it can make it to just that very corner of the shed, but not past it. And in fact, the same thing, it bugs me because it's a little bit too big. And then the same thing would happen in the other direction. If the goat tried to come over here, it would be able to get to this point, but nowhere past that. So what we come up with is an area that the goat can travel. Yeah, and again, that other one's kind of bugging me. What happens if I just try to make it? I won't do that. It should intersect that top of that other circle. It's just a little bit harder to do with the devices that I have. Let's call it right there. That looks okay. All right, so that's what we're looking at for the area, but all I see here is just a bunch of circles and some red lines. So where can it go? Let's look at that using a highlighter. Okay, so basically it can go where all of these, I don't want to say where all these circles overlap, but where the big circle intersects with the smaller circles at their respective spots. So it can't touch the shed, but it can hit all of this circle, right? And so everything in there. It can hit everything in this circle that's not the shed. And then it can touch everything in the big circle that's sort of to the lower right of those other two circles. So it can go anywhere up here. And so I'm actually going to leave this one here and let you finish it. From here, it just depends on knowing the area formula for a circle, which I think you can handle. Okay, you're looking at, and I guess you do have to sort of decide for yourself how much of each circle do you count for area, and you can go with either an addition approach or a subtraction approach. I would recommend addition though, because I would say that goat can reach, this is how I would lay it out. From the big circle, it gets this area right here, which is 3/4 of a circle. So it gets 3/4 of the big circle, and then it gets, in addition to that, an extra 1/4 of each of these small circles. So I'll let you go with that idea and try to figure it out. So for the next one, we're looking at the allowance problem. And my recommendation was to look at this in three kind of categories. Because obviously for the first option, it's just $1,000 on the 15th. Is that good or is that bad? On the second option, you get a penny on the first day, 2 on the second day, 4 cents on the third, and it continues to double every day. So I looked at day, the amount received, and then the total. And in class, I showed this in an Excel spreadsheet. I'm just going to do a couple of the days here and then let you continue with the rest of it. So on day 1, we get a penny. So our total's a penny. On day 2, we receive double the amount from the day before. So we have 3 cents. Day 3, we get 4 cents. So we have 7 cents. Day 4, we get 8 cents. So we have 15 cents. Then we get 16. So we have 31 cents. 32. 63. Nope. So then we have, I think, 127, and that process continues. So we're almost a third of the way through the month and we have $1. I'll do a couple others, I guess. We get $1.28. So that's going to be $2.55. And then we get $2.56. 4, 5, 12, so $5.11. And that's what we get at the end of day 9. We've got $5 at day 9. Probably have about $10 on day 10. So it took you 10 days to earn $10, or on the 15th you can just take $1,000. It's up to you. But for this process, it goes 30 days. So our end goal would be to see how much we have and receive on June 30th. Okay? So go ahead and give that a shot. I think that you can handle that one from there. Use Excel if you have to. It makes life a lot easier. Even if you don't know the function that this is, the quick way to to do it, you can just say, for this cell, for this day 10, in Excel you can say, take this day, multiply it by 2, and then you can just drag that down, and it'll keep doing it for you. And for this day, I would say find the sum of these cells, and I think you can probably make that work. Or you can do it day by day, figure out how much you have. Okay. The next one we talked about was paper tubes. Just saying that I give you just a normal piece of notebook paper. It could look like this. And we have a couple different ways that we can turn it into a cylindrical tube. We go this way. This would make the one on the right. Yes, the one right below me here. And then this other way would make the first one, the 11-inch height. And so the question is, which one gives the, this question is, what is the ratio of the two volumes? I would just say which one's bigger. Which one would hold more would be a decent way to think about that. The problem is these two pictures only give us one dimension or one measurement. So for that first one, as I fold it this way, I actually know another one of the measurements. I know what this circumference would be. This circumference up here would be 8.5, and similarly on this one, its circumference, great picture, would be 11 inches. Okay, so let's go ahead and check the volumes. So the volume of this one, volume of a cylinder, is area of the base, which is pi r squared, times the height. The radius is 8.5, so, sorry, the radius is not 8.5, that's the circumference. We do need to find the radii of these two given the circumference. So circumference, if you remember, is pi times the diameter. That doesn't help me too much, but what does help me is to know that it's also 2 pi times the radius. Let's solve for the radius knowing what the circumference is. So if I just do divide by 2 pi, I know that the radius would be the circumference divided by 2 pi. And in this problem, it actually doesn't matter what you use as pi. As long as you use the same thing, you will get the same ratio. You might not get an exact volume to whatever level of accuracy you want, but you're going to know which one's bigger, let me put it that way. So for the first one, my circumference is 8.5, and I want to divide that by, I'll use my pi button. So that's 2 pi right there. No, that didn't work. Okay. Let's do it this way. Let's go We'll just use 3.14. No, I should be able to do it with my parentheses. Divided by, maybe that was my answer. See, I don't like that it's saying divided by, okay. Let's try one more time. I think the pi is negating the, yeah, that's what was happening. So I get 1.35. So this one has a radius of 1.35. This one over here has a radius of, let's do that same thing with 11. So 11 divided by 2 pi, 1.75. And we'll figure out the volumes. So this one is 62.98. For this one, I'm going to have pi 1.75 squared times 8.5 and this one is 81.78. Okay, so the one on the short and wide cylinder holds more. Okay, for the next one, more volume stuff, which is good. These two problems kind of work together. So it says here that a tennis coach told Alice if she wanted to be the #1 singles player, she would have to answer this problem. It says, in a can of tennis balls exactly 3 high, which is greater, the volume of the balls or the volume of the air around the balls? If you don't know, a can of tennis balls is pressurized to where the air is pushing against the balls. It helps until you break that seal, but it helps sort of keep the balls have the bounce that they want to have. And we want to not worry about how thick the balls are. And when we're talking about the volume of the tennis balls, we're talking about the rubber outer and the air on the inside, because they are filled with air. But what should Alice's answer to the question be, assuming that she wants to be the #1 seed? That's a want to right there. So we're going to look at a couple different things. We're going to start off by finding the volume of the entire can. So this isn't the volume of the air. This isn't like just this volume right here, all these. Even though this is what we want to eventually find, we're not there yet. We're going to find the total volume of the can, so that's including the balls, all that stuff. And so it's a cylinder. We just found the volume of cylinders, so that's going to be pi r squared times the height. We're going to really work with this problem in terms of the radius of a tennis ball. We don't know what that radius is. We could probably find it, but we're just going to work with that as being just an unknown that we're not going to really know. The best thing about it is that in a can of tennis balls, the top of the top ball touches the lid, and the bottom of the bottom ball touches the bottom. They just exactly fit in there. So, what does that mean for the height of the can? First of all, obviously the radius of the tennis ball is also the radius of the can. That I should have said first. So, whether you consider this to be the radius of the ball or the radius of the can, it's the same thing. Okay, and maybe I write that the radius of a tennis ball is going to equal the radius of the can. But what is the height? To figure out the height of this tennis ball can, we're going to count the number of radii, make it. Here's 1, 2, 3, 4, 5, 6. So the height here is equal to 6 of the radiuses, the radii. So for the volume of the can, we can simplify that to be pi r squared times 6r. When we simplify that a little bit, we're going to end up with 6 pi r cubed. Okay, that's good. Let's find the volume of one ball. I should say one ball. Because eventually we're going to have to find the volume of 3 balls, but that's a little bit easier. So the ball is in the shape of a sphere, and so that's 4/3 pi r cubed. And that's all we needed. The volume of, I don't want to write it that way, the volume of 3 balls that just barely fit in the can is going to be 3 times this, or 4 pi r cubed. So that tells us that the volume of the air is equal to the volume of the can minus the volume of 3 tennis balls. And we have equations for both of those. 6 pi r cubed minus 4 pi r cubed is equal to 2 pi r cubes. So which one's bigger, the volume of the tennis balls or the volume of the air? The tennis balls win it. So it's interesting. For the last of the 6 tasks we're talking about, it looks like a systems of equations problem. Okay, let's go ahead and break down what's going on. So Eric was out to lunch one afternoon at a deli, and he bought 3 or he didn't buy, but the menu shows 3 sandwiches, 7 cups of coffee, and 1 piece of pie. Cost $13.95. The menu also shows a combination of 4 sandwiches plus 10 cups of coffee plus the same piece of pie is equal to $18.60. Now this would be a really easy problem if they gave us one more set of like one more combination of the 3 items. The problem is it doesn't. So we have to kind of figure that part out. So here's how we're going to look at this. And what we want to find is, we want to find what is 1 sandwich, 1 cup of coffee, and 1 piece of pie cost. So we're actually going to start off by subtracting these 2. Because I do know that if I subtract them, I get rid of my pieces of pie. But actually some more stuff happens. I get, weirdly, -1 sandwich plus 3 cups of coffee is equal to negative, what is that? Let's get that. 13.95 minus 18.6. 465. Not really helpful with the negatives. Let's go ahead and move those negatives. Let's say that 1 sandwich minus 3 cups of coffee is equal to 465. That looks a little bit better. okay? And that's fine, but not really as helpful as I wish it was. So we need a way to sort of manipulate this and get rid of some other things. Okay. Oh, I guess this is probably incorrect here. This would be minus 3 cups of coffee, so this would be plus 3 cups of coffee. But we do want to, we still are at the same issue. So I'm going to do this. I'm going to take equation 1. I'm going to multiply that by, I'm going to try to eliminate s's. So I'm going to multiply it by negative 4. Because I do like addition better than subtraction. So I'm going to multiply that by negative 4. I'm going to get negative 12 sandwiches. Let's see, minus 28 cups of coffee minus 4 pieces of pie is going to be $13.95. Why did I do that? I don't know. Multiply it by 4, negative $55.80. And then I'm going to take equation 2 and I'm going to multiply it by 3. Because again, I'm trying to get rid of s's here. I get 12s plus 30 cups of coffee minus 3 pieces of pie, and that's going to be 1860 times 3. Wow, that one's also 55.8. So when I add these two equations here, I'm going to end up with 0 sandwiches, 2 cups of coffee, and what did I not do there? Oh, I don't know why I subtracted that. Okay. And negative 1 piece of pie equals $0. That almost seems unhelpful, except for the fact that 1 piece of pie, I now know is the same amount, costs the same amount as 2 cups of coffee. Solving this equation for P, I guess. Okay, and that's a big piece of information. In fact, I can use that right up here. And here's how I'm going to use that. This is a very tricky problem because of this one trick right here. If I look at this bottom equation right here as a sandwich plus a cup of coffee plus 2 cups of coffee, because 1 cup and 2 cups would be my 3 cups, that equals $4.65. But what is the same cost as 2 cups of coffee? 1 piece of pie. So there is a hidden way to solve a system of equations with 3 unknowns but 2 equations. The trick with this is we didn't really solve anything. I don't know how much I don't know how much a sandwich costs. I don't know how much a cup of coffee costs, and I don't know how much a piece of pie costs. I can relate the two. I can compare the two. I know that a sandwich is equal to $4.65 minus 3 cups of coffee, but that's just a relation. That's not a solved equation. Okay, so that's it. That's the last of our 12 tasks. Make sure that you pick one of those to make a video on or some kind of a presentation on. It can be PowerPoint, I guess, but I would ask that you do some work figuring out how to narrate a PowerPoint. I'm not picky about how the video looks. It does not have to be done on a computer. You could sit there with a piece of paper and have somebody in your family record over your shoulder. That would be just as fine. Okay. Or, like I said, find a way to get creative and make this problem your own. Make it something that you're proud of. I'm very proud to have put each one of these problems in. I think they all hold some sort of a problem-solving aspect, and they're not your everyday run-of-the-mill problems. I hope that helps. Have a good day, and we'll see you in class.